I want you to imagine, just for a second, the sheer crushing weight of a mining dragline.
Oh yeah, those things are just massive.
Right, like, we are talking about an earth-moving machine that is so ridiculously large, it actually walks on these massive steel pontoons. It drags a bucket that's literally the size of a two-story house.
It's hard to even wrap your head around that scale.
Exactly. Or, picture the absolute scorching environment inside a steel mill. Molten metal is just radiating this unbelievable, terrifying heat, and these massive steel rollers are just glowing red.
Yeah, the physical extremes in those places are wild.
So when you really picture those extremes, you kind of have to ask yourself, how does all that moving metal not instantly just grind itself into, like, fine metallic powder?
Well, I mean, we tend to look at these massive industrial machines, and we just assume their sheer size and bulk protects them.
Because the visual is so imposing.
Right, exactly. But the physical reality is actually entirely the opposite. The bigger the machine, the greater the gravitational and mechanical forces that are actively trying to tear it apart.
Yeah.
I mean, metal fundamentally wants to grab onto other metal.
And the answer to how it actually survives is hidden inside a stack of highly detailed technical data sheets that we're looking at today. They're from Whitmore, which is a manufacturer of extreme service lubricants.
And this is such a cool topic.
It really is. Our mission for this deep dive is to decode the hidden microscopic chemical engineering that quite literally keeps the modern industrial world spinning.
Because, I mean, these data sheets, they might look like dense walls of numbers and viscosities and obscure laboratory test results at first glance.
It's just a bunch of jargon.
Yeah, exactly. But if you know how to read them, they reveal this completely fascinating hidden world where organic chemistry basically goes to war with extreme physics.
Okay, let's unpack this. Because if you are anything like me, you probably hear the word grease, and you just think of some generic black goop in a tube. You know, the stuff you use on a squeaky door hinge or a bike chain.
The stuff you buy at the hardware store.
Exactly. But what these documents show is that industrial grease is not goop, it is highly engineered armor.
Armor is the perfect word for it.
Yeah. But before we even get into the specific products, we should probably establish what grease actually is, chemically speaking, because it's not just thick oil, right?
No, that is a really crucial distinction. Grease is generally made of three components. You have the base oil, which is the actual fluid doing the lubricating work.
Okay, that makes sense.
Then you have the thickener, which you can think of as a microscopic chemical sponge that just holds that oil in place.
Like a sponge holding water.
Exactly. And finally, you have the additives. These are the specialized chemical weapons mixed in to fight very specific threats. So, just like medieval armor, different environmental threats require entirely different metallurgical and chemical defenses.
That is so cool. Okay, so let's start with the most fundamental enemy of heavy machinery, which is crushing physical pressure. Just brute, unrelenting force.
Heavy hitters.
Right. You've got that massive earth-moving shovel we talked about. It's digging into solid rock, and all that weight is bearing down on just a few pivot points and bucket pins.
This is exactly where we see Whitmore's caliber 3M and 5M greases step into the ring. These are lithium complex greases designed specifically for draglines, shovels, and heavily loaded rolling stock.
And that M in the name is the really critical part, isn't it?
It is. It stands for molybdenum disulfide, which engineers commonly just refer to as MOS2.
And the number, so the 3M and 5M, that just refers to the actual percentage of MOS2 added to the grease, right? Like 3% or 5%.
Spot on.
Yes.
But let's get into the why. Why are they adding this specific compound? Like, what does it actually do? Well, the physics behind MOS2 is actually brilliant.
Yeah.
When you have two massive steel components pressing against each other with literally tons of force, the base oil in the grease, the liquid part, can actually be squeezed right out of the microscopic gap between the metals.
Because the pressure is just too high.
Exactly. And if that happens, the protective film breaks. You get metal-on-metal contact.
Which is bad.
Extremely bad. That microscopic bruising is exactly what we call scuffing in the industry, and it's basically the beginning of the end for a machine. You get heat spikes, metal tears, and eventually a catastrophic failure.
Which means incredibly expensive parts replacement and massive operational downtime. But zooming way in on molybdenum disulfide explains how it prevents this.
Right.
If I'm understanding this, you can think of MOS2 molecules like millions of microscopic ball bearings, or maybe like tiny flat playing cards distributed all throughout that chemical sponge.
That's a great analogy, yeah.
So even if the liquid oil gets physically pushed aside under a massive shock load, those microscopic solid particles get left behind in the gap. They act as a sacrificial barrier. They basically take the bruising so the steel doesn't have to.
Yes, that structural sacrifice is the key to the whole thing.
Yeah.
But, OS2 isn't the only way to build that armor. The datasheets also detail a product called Caliber Blue EP.
Right, I saw that one.
Yeah, and it takes a radically different chemical approach to solving the exact same problem.
Because Caliber Blue doesn't use MOS2 or graphite at all. Instead, it uses this proprietary blend they call SL Tech.
Right, SL Tech is a really carefully engineered blend of light-colored, solid lubricants. So instead of acting like tiny ball bearings, it forms this highly protective, continuous cushion over the metal asperities.
The asperities.
Those are the microscopic jagged peaks on the surface of the steel. Because even smooth steel isn't perfectly smooth at a microscopic level.
Oh, okay, got it.
So it coats those peaks. And it actually provides greater extreme pressure properties than traditional MOS2. But crucially, it achieves this without containing any heavy metals or environmentally hazardous ingredients.
So it's basically a liquid suit of armor that's much safer for the environment if it ever leaks out. That seems incredibly versatile for, like, slow to medium speed equipment.
It definitely is.
But reading through the datasheet, there is a very strict warning slapped on this stuff.
Yes. And what's fascinating here is that you would naturally think, wow, this Caliber Blue is incredibly strong and environmentally safe. Let's just use it to lubricate literally everything in the plant.
That would be my first thought, yeah.
But the datasheet explicitly states that because of its high base oil viscosity, you should never ever use it in electric motor bearings.
Which feels super counterintuitive. I mean, if it protects so well, why would it destroy an electric motor?
Well, it's a perfect example of how hyper-specialized these formulations have to be. Viscosity is fundamentally a measure of internal fluid friction. It's how much a fluid resists flowing. So imagine you're trying to run through waist-deep water, and then imagine trying to run through waist-deep mud.
Big difference.
Huge difference. If you put a grease with a very high base oil viscosity, which is the mud in this scenario, into a really fast-spinning electric motor bearing, the motor has to use an enormous amount of its own energy just to push the grease out of the way.
Oh, wow. So the motor is literally fighting its own protection.
Exactly.
The internal drag causes the temperature to spike, the electrical components overheat, and the whole thing just burns out. You basically suffocated the bearing.
That is the exact mechanism of failure. You really can't just slap the toughest grease on everything. You have to balance the chemical viscosity against the mechanical speed of the machine.
That makes total sense. And speaking of finding that balance for really tough jobs, we have to mention Caliber XR and XR Syn, because the text literally calls XR the most robust lithium-based grease in their entire line.
Oh, absolutely. XR is the heavy hitter. It's reserved for severe continuous loads and really extreme shock loads. We are talking about things like steel mill roll stands.
Or the slew rings on forestry equipment that lift 1,000-pound trees.
Yeah, exactly. And then the XR Syn version levels up by using full synthetic base oils instead of conventional mineral oils.
So what does that synthetic difference actually mean at a molecular level? Like, why does it matter?
Well, conventional mineral oil is refined straight from the ground, which means its molecules are all sorts of different shapes and sizes.
And it's inconsistent.
Right. But synthetic base oils are built in a lab from the ground up. Every single molecule is uniform. And because they are uniform, they don't thin out as quickly when the heat spikes, and they don't thicken up into a sludge as quickly when the temperature drops.
It provides that really crucial dual threat capability. But let's shift our focus a bit, because we just established how chemical engineers fight physical pressure and shock loads. But what happens when the environment itself goes on the offensive?
Oh, that's a whole different ballgame.
Because you have these massive machines operating outside, entirely exposed to the elements.
Yeah, that brings up a massive engineering headache. When water or extreme freezing temperatures enter the chat, the chemistry has to perform entirely different tricks.
Right, so let's tackle the threat of water first. Looking at the specs for Compass EP, I actually have to push back on the core concept here.
Okay, let's hear it.
Well, we've all been taught since kindergarten that oil and water simply do not mix. They actively repel each other. So how can a grease, which is largely comprised of oil, actively survive high-pressure water spray in places like wastewater treatment facilities or marine locks? Shouldn't the water just blast the oil right away?
Honestly, it would if it were just oil. But this comes right back to that thickener system and those specialized additives we talked about.
Okay, so how does it work?
Compass EP is a lithium-calcium grease, and the engineers fortify that sponge-like structure with these synthetic polymers.
And how do those polymers act mechanically to actually stop the water?
Think of synthetic polymers like microscopic Velcro, or maybe long, tangled chains.
Hmm.
When they are milled into the grease, these polymer chains physically intertwine with the microscopic pores of the steel surface.
They grab on.
Exactly. They make the grease fiercely adhesive. So when a blast of high-pressure water hits the machine, the mechanical structural integrity of those polymer chains just refuses to let go of the steel. The water basically hits a wall.
And that structural integrity is tested in a way that just sounds punishing. The datasheet details this 5,000 strokes laboratory test.
Yeah, the bench tests are brutal.
They literally intentionally mix water directly into the Compass EP grease, and then a machine essentially beats it and churns it for 5,000 strokes. And the result?
There is zero measurable effect on the grease's physical consistency. It just stays intact.
Which is wild because the text notes that under this exact same test, conventional greases completely break down. Their molecular sponge collapses, and they become soft, basically flowing away like soup.
Yeah, they just wash out. But we do have to account for reality here. Eventually, water does inevitably find its way into the body of the grease over long periods of time. You can't stop it forever.
Right, it's operating in a marine lock or something.
Exactly. But Compass EP has specific chemical additives designed to chemically manage the water that breaches the perimeter. It essentially isolates the water droplets so they can't cause rust.
And it is still handling extreme physical pressure while doing all this water management, which is crazy. The 4-ball machine test data on this product is incredible.
Oh, the 4-ball EP test is a brutal industry standard.
Tell me about it.
They take 3 steel balls, lock them together in a really tight triangle, put a 4th steel ball directly on top of them, coat them in the grease, and then spin that top ball while applying heavier and heavier mechanical loads.
Just grinding them together.
Right. They keep adding pressure until the friction generates so much heat that it literally welds the metal balls together into one solid ruined chunk.
And Compass EP hits a weld point of 500 kilograms on that machine. To put that 500 kilograms in perspective for you, that is the equivalent of balancing a grand piano on the tip of a ballpoint pen.
That is a lot of pressure.
And the microscopic oil film still doesn't break. It's doing 2 incredibly difficult jobs, pressure and water at once. But water isn't the only environmental enemy out there. Let's talk about ice.
Yeah, ice changes the viscosity equation entirely. How do you push something thick and protective through tiny lubrication lines when the temperature drops to the point where normal oils basically turn into solid wax?
Enter Legacy M. This stuff is designed for mining equipment operating in freezing conditions, and the text says it is pumpable all the way down to negative 50 degrees Fahrenheit.
Which is negative 46 degrees Celsius, for the record.
Just think about trying to start a standard car when it's just 10 degrees below zero. The oil gets super thick, it's sluggish, the engine whines. Now scale that up to a 100-ton machine in the Arctic Circle.
To really understand how extreme that negative 50-degree rating is, look at the Lincoln vent meter test data provided in the specs. The vent meter specifically measures the physical pressure required to push grease through a really long coiled restriction of tubing at plummeting temperatures.
So it simulates the automatic greasing lines winding all over a massive machine.
Precisely. And Legacy M passes this low-temperature pumpability test at negative 40 degrees. It achieves this by using an aluminum complex thickener system.
Okay, an aluminum complex.
Yeah, the molecular structure of this specific aluminum complex ensures that the grease maintains a really smooth, buttery texture. It refuses to crystallize, which is what allows automatic lubrication pumps to actually push it through the lines when you're dealing with hard conditions.
Because if the automatic greaser freezes up and blocks the line, your mining machine is running totally dry, and then you're right back to that million-dollar metal-on-metal nightmare we talked about at the very start.
Right, the machine destroys itself before the operator even knows the grease line is frozen.
Okay, so if water and ice are huge environmental hurdles, what about active chemical attacks and scorching, unrelenting heat? Like environments that would literally dissolve or vaporize normal materials.
Now we are looking at the true extremes of industrial chemistry. And the Whitmore lineup, the absolute superhero here, is Matrix EP.
And here's where it gets really interesting, because Matrix EP isn't just a physical barrier holding oil. It abandons lithium and aluminum entirely for a totally different thickener system. calcium sulfonate complex.
Calcium sulfonate is such a magnificent molecule. We talked earlier about thickeners basically acting like a sponge just to hold the oil in place.
Right.
But calcium sulfonate acts as the sponge and is a highly active protective agent all by itself. It is a massive multitasker.
The way I picture it, calcium sulfonate molecules are shaped almost like little chemical tadpoles. The heads of the molecule have this incredibly strong polar attraction to metal, so they latch onto the steel surface, forming this dense physical wall, while the tails kind of stick out.
That's exactly it.
And those tails literally catch and neutralize acid molecules before they can ever reach the steel.
It creates an active chemical shield. The text explicitly states that matrix EP neutralizes acids, preventing corrosion despite years of continuous exposure to things like phosphoric acid fumes.
Wow.
It just refuses to react with caustic materials. And then you look at the thermal stability. The temperature data on this just defies logic.
It can handle a continuous operating environment of 400 degrees Fahrenheit, that's 200 degrees Celsius, and it can push to a continuous 550 degrees Fahrenheit if you replenish the bearing with fresh grease every 30 minutes.
But the real shocker is the temperature spikes. It can sustain spikes of 600 degrees Fahrenheit for 5 to 10-minute periods without melting or carbonizing.
600 degrees. I mean, most normal oils would have literally smoked off and oxidized, turning to hard black carbon.
And carbon acts like microscopic sandpaper inside a bearing.
Exactly, destroying it from the inside out. But the calcium sulfonate structure just holds together. And wait, do you remember that rule we talked about earlier with caliber blue? The strict warning about never putting it in an electric motor due to internal drag.
Oh yeah, the high viscosity suffocation.
Well, the Matrix EP datasheet points out that Matrix EP2 is actually the preferred, recommended grade for electric motor bearings. It says it can handle DN speeds up to 250,000.
Let's define that, because DN speed is a crucial calculation for engineers. You take the inner diameter of the bearing in millimeters, and you multiply it by the motor's RPM, which is revolutions per minute.
Okay, so diameter times speed.
Right, so a DN of 250,000 means you have a reasonably large bearing spinning at just blinding, dizzying speeds.
So this single product survives phosphoric acid, doesn't burn at 600 degree spikes, neutralizes rust, and can spin at blinding speeds without causing drag.
And if we look at the anti-wear mechanism, the text notes the thickener system in Matrix has a protective effect very similar to molybdenum disulfide.
The ball bearings from earlier.
Exactly. It protects equipment from wear under heavy load and slow speeds, but it mimics that MOS2 ball bearing effect through an entirely different chemical pathway using the calcium sulfonate structure. It is really a masterpiece of chemical engineering, solving multiple extreme problems simultaneously without relying on heavy metals.
It really is the Swiss Army knife of extreme environments. Okay, so we've explored the most toxic, freezing, scorching, and brutal environments, but there is another extreme we haven't touched on yet, and it's one that impacts literally everyone listening to this right now. What happens when heavy industrial machinery intersects with the food you eat?
Yeah, this is where the engineering constraints become incredibly delicate and highly regulated.
Imagine the sheer anxiety of being the chemist tasked with this. You have to make a product that survives those crushing metal-to-metal shock loads we discussed, resists being washed away by high-pressure boiling steam, but must also be entirely, completely safe if a microscopic amount accidentally drips onto a conveyor belt carrying, like, chicken nuggets or baked goods or packaged bread.
This is the domain of Medallion FM, where FM stands for food machinery.
The very first thing to note is that it is NSF-H1 registered. Let's clarify what that means. That is the official global designation for lubricants approved for incidental food contact.
Incidental being the key word.
Right. You aren't cooking with it, obviously, but if a tiny fraction of a drop makes it into the food supply, it will not cause harm.
But the datasheet reveals details that go far beyond just a basic governmental safety rating.
This is the part that completely blew my mind. The production of this heavy industrial grease is produced under the supervision of Dallas Kosher. It is certified kosher Parev for year-round use and is specifically noted to be acceptable even during Passover.
Right, and if we connect this to the bigger picture, industrial lubrication isn't just about preserving capital equipment or keeping factory lines from breaking down.
No, it touches everyday life.
Exactly. In the food sector, this chemistry is intrinsically tied to public health, rigorous safety standards, and deeply held religious dietary laws. A single breakdown in the chemical formulation or cross-contamination at the lubricant factory could violate thousands of years of dietary tradition or trigger a massive nationwide food recall.
And it still has to do its day job as armor. The text points out it is highly water resistant to survive the constant daily high-pressure washdowns in food plants. Plus, it contains an NSF-approved preservative specifically engineered to limit the growth of bacteria within the grease itself.
It is fighting mechanical friction and microscopic microbes at the exact same time.
It's incredible.
It really is. It is formulated to be highly adhesive, so it sticks to the metal machinery, and cohesive, meaning the grease molecules stick firmly to themselves.
Yeah.
That cohesion is how it resists pounding out of the bearings during shock loads.
Just holds itself together.
Yeah, it stays exactly where the maintenance team puts it, which is the absolute most critical factor when food is being processed mere inches away.
Now, we've been talking heavily about the grease on the conveyor belt bearings and the exposed pivot points, but what about the massive gearboxes actually driving those belts and machines? We need to transition here because while we're talking about specialized defenders, we really should touch on one product in our stack that operates under a completely different set of physics, Multiplus.
Ah, yes. That requires a complete shift in how we think about the fluid dynamics here. Multiplus is a gear oil, not a grease.
Okay, so no sponge.
Right, no sponge. You are moving from a grease, which is designed to stay put, to a fluid gear oil designed for enclosed systems. Think industrial gearboxes, automotive differentials, and transmissions. The oil is a pure liquid, violently flowing and splashing around the gears.
It's a chaotic environment, and Multiplus has some very specific chemical properties to handle that enclosed violence. Two properties really stood out in the text: its anti-foam capability and its rapid demulsification. Let's break down the foam first. Why is foam dangerous inside a gearbox?
Well, when steel gears are spinning at high speeds in a closed bath of oil, they basically act like a massive blender. They whip air into the fluid, creating foam. But foam is mostly trapped air.
And air is not a lubricant.
No. From an engineering standpoint, air is a terrible lubricant. Furthermore, air compresses under pressure, whereas oil does not. When those air bubbles get caught between two mashing gear teeth, the air compresses rapidly, which actually generates micro-explosions of intense heat.
Oh, wow. So the foam literally burns the oil from the inside.
It does.
The text highlights that Multiplus has chemical additives that instantly break the surface tension of those entrapped air bubbles as they form. It collapses the foam back into pure liquid, which protects the seals and keeps operating temperatures low.
And then you have the rapid demulsification property.
Right.
If condensation or outside water gets into the enclosed gearbox, the oil separates from it quickly and completely. It refuses to emulsify or blend with the water to create a milky sludge.
Because, again, as the text notes, it does not lose its lubricity due to emulsified water. It chemically isolates the threat, allowing the pure oil to keep protecting the gears while the water sinks to the bottom where it can be safely drained off.
It manages the closed ecosystem perfectly.
So what does this all mean? We have journeyed through a microscopic world of lithium complexes, aluminum complexes, calcium sulfonate tadpoles, most stew playing cards, and SL Tech armor. We've gone from the negative 50 degrees Fahrenheit deep freeze of a mining pit to the 600-degree spikes of an industrial oven.
We've covered a lot of ground.
We really have. We've survived phosphoric acid fumes, 500-kilogram weld points, high-pressure water jets, and we've even maintained strict kosher certification.
I think what it means is that the massive, imposing physical world around us is genuinely held together by invisible, microscopic chemical forces.
These chemical formulations really are the unsung heroes of the modern world. Without these incredibly precise, hyper-specialized molecular structures, everything we take for granted would literally grind to a halt. The metal would just eat itself.
You know, I want to leave you with a final thought on that. Consider the concept of friction in a broader philosophical sense. We spend so much of human history trying to eliminate friction.
That's true.
We try to eliminate social friction to build peaceful communities. We try to eliminate digital friction so our software runs smoothly, our packages arrive overnight, and our data moves instantly. We want everything to be seamless.
But physical friction is always waiting in the wings.
It is.
Okay.
Physical friction, the grinding, tearing, thermodynamic reality of two massive objects colliding is the most basic, primal force trying to tear down everything we build. So the next time you see a massive skyscraper being erected with huge cranes, or you start your car on a freezing morning, or you simply eat a piece of perfectly packaged food from the grocery store, think about this.
Yeah.
Our entire heavy industrial civilization balances on a microscopic, highly engineered chemical film that is often less than a single millimeter thick. Without that microscopic layer of chemical defense, the friction wins and the world literally stomps.
That is a staggering way to look at it. From the crushing weight of that drag line to the delicate hygiene of a food plant, it all comes down to the brilliant chemistry happening in the microscopic gaps. Thank you so much for joining us on this deep dive into the hidden world of extreme lubrication. Keep looking closer at the invisible systems around you, and we'll see you next time.